Alright, so I wanted to do a little demonstration. This is actually a demonstration you can do at home. You have been doing these at home, right? In fact, this is on page 167 of your textbook, and it's pretty simple. All you need is 3 cups and some water. So I've labeled my cups. We've got cold over here, I got warm, and I've got hot. And be careful, don't make your water too hot. I've got mine, I threw mine in the microwave, and so it's actually kind of on the upper limits of what I'm willing to tolerate. But following the instructions in the book, all you have to do is just stick your fingers, 2 fingers, or one finger from each hand, in your hot and your cold cups, and give them a few seconds to kind of acclimate. And again, depending on how hot or cold you've made your water, maybe tough to stand it, but you give them a little bit of time to get oriented to those temperatures. And then once we've gotten sort of acclimated, then we're going to put them in the warm cup. That feels all right. And so then you put them both in the warm cup. And again, give them some time to acclimate and see if there's a difference in the sensation you get in each finger. And I find it's somewhat useful to kind of wiggle them around a little bit to really pick out the different sensation that you're going to experience from each finger. And essentially this whole activity is to point out that sometimes our senses aren't necessarily reliable. You may wind up getting different information from your 2 fingers despite the fact they're both in the same cup of water. And so it's really kind of an interesting experience. So I encourage you, I'm not going to tell you what I'm feeling here, because you should be trying it on your own, shouldn't you? And you're a scientist after all, aren't you? You want to have evidence. That is the ultimate guide to a scientist's thinking. Evidence. And if it's evidence you can collect directly yourself, that's the best kind. All right, get to it. Okay, so I wanted to first of all get to the definition of temperature. Temperature is defined as the average kinetic energy of a substance. And if you recall, if we think back to Module 3, when we defined kinetic energy, remember, kinetic energy is energy of motion. And so you might think, well, gosh, how would I describe the temperature of a helium balloon? Let's just imagine a helium balloon just kind of sitting there on a string. If you think about kinetic energy, you say, well, gosh, the balloon is not moving, so it has no kinetic energy. Remember, we said kinetic energy is energy of motion from Module 3. In Module 3, when we were describing the kinetic energy of an object, we were talking about the motion of the entire object, what I like to call the macroscopic motion. So the entire object, if it's moving, it has kinetic energy. If it's not moving, it doesn't have kinetic energy at the macroscopic level. However, that helium balloon is made up of a bunch of helium molecules inside that balloon. And even if the balloon itself is at rest and it has no macroscopic kinetic energy, that's not to say that all the parts of the balloon are not moving. Those helium molecules are zipping around and they're vibrating and they're spinning and all that kind of stuff. So they actually are moving at the microscopic level. And that's what we're talking about when we talk about temperature. We're not talking about the kinetic energy, the macroscopic kinetic energy of the object. We're talking about the microscopic kinetic energy, rotational energy, potential energy of the atoms or molecules that make up the object. So that's a very important distinction to make. So therefore, an object, whether it's a gas, it could be a glass of water, a liquid, it could be a bowling ball, a solid, just sitting there. Even if they're not in motion and therefore have no macroscopic kinetic energy, they can have microscopic kinetic energy because of the motion of the atoms and molecules that they are composed of. So what do we use to measure temperature? We use thermometers, and the word thermometer probably brings to mind a liquid in glass thermometer. That's the one we're most familiar with, I would imagine. But it's important to think about what's actually going on in a liquid in glass thermometer. When you stick that into your mouth, or if you stick it into a beaker of hot water, what's actually going on? It turns out, and we're going to be talking about this in the next few slides, the thermal energy from the hot water or from your mouth is transferred to the glass as well as to the liquid that's in the glass. And those different substances, the glass and the liquid, let's say it's an alcohol on the inside, in the inside of the glass, respond to that increase in energy a little bit differently. They both gain energy, and they both therefore expand. There's a principle called thermal expansion, which we'll be discussing shortly, but it's pretty common sense that most things, most substances, when they get warmer, they get bigger, they expand. And when things typically get colder, they contract, they get smaller. So when you put that liquid in glass thermometer into a hot liquid, the glass and the liquid inside are going to expand. But it turns out they don't expand in equal amounts. The liquid inside expands at a greater rate than the glass does. And therefore, that's why you're able, because that liquid starts to expand really fast, it starts to climb up the tube inside that's formed by the surrounding glass. And the liquid is expanding more than the glass is itself, and therefore you see a rise in the liquid level. That's how a liquid and glass thermometer works. You may also be familiar with thermometers that have like a needle to them. Quite often these are outdoor thermometers that you might have outside your window to see how cold or how warm it is outside. These things operate not with liquid, but with a little coil of wire in the back. If you ever check one out, it's a little coil of actually, well, not wire, it's a little metal coil. And it's actually made of what's called a bimetallic strip. It's a strip that has two different types of metal, and the metal, of course, when it's warm, expands. When it's cold, it contracts. And so that is the expansion or the contraction of that coil then causes, that's attached to the needle, and it causes the needle to go up or down. So again, it's a thermal expansion, this time not of liquid, but rather a thermal expansion of this little coil of metal that causes the needle to go up or down. You may also be familiar with thermometers that have just a digital readout. Quite often, modern thermometers that you stick under your tongue might not even have a liquid that goes up. It just has a little digital readout. How do those work? It turns out it's not expansion of a liquid or a metal in this case, but rather an electronic circuit inside the thermometer. It turns out that electronic circuits have things called capacitors, and capacitors are temperature sensitive. So essentially, when you expose the electronic circuit to a change in temperature, there's going to be a change in capacitance in the circuit, which is then going to be, that's how you're going to get the temperature readout, is because the capacitance within the circuit is changing, and therefore that's how you get your display. For better or worse, America is stuck with the Fahrenheit temperature scale, but of course we are a rarity in the world. So this skill builder I encourage you to check out. This will teach you a little bit more about not only the Fahrenheit scale, but also the Celsius scale and the Kelvin scale. It turns out that the Kelvin scale is the preferred temperature scale in science. So if you ever study a lot of science, you're going to see a lot of values in Kelvin. So it's kind of good to get comfortable and familiar with the different temperature scales. And the one challenge in this skill builder is for you to figure out what temperature is the same on both the Fahrenheit and the Celsius scales. Who knows, you might show up on Jeopardy someday and be asked this question. So can you figure out at what temperature the Fahrenheit and the Celsius scale are the same? It would be being outside at this temperature, you get the same reading on both the Fahrenheit and Celsius scales. One of the reasons that the Kelvin scale is so useful is that it's got a 0 point that really means something. The 0 Fahrenheit or 0 Celsius, let's take that for example, is the freezing point of water. But even when you go below 0 Celsius, we're talking about ice or things that are that cold. The atoms and molecules that make up the ice are still moving around. So there is still thermal energy involved there. And so the 0 Celsius doesn't help us very much. 0 Fahrenheit, same thing. You can get below 0 Fahrenheit, and yes, it's going to be cold, but the atoms and molecules are still going to have energy. The beauty of the Kelvin scale is that its 0 is when everything stops. Even the molecular and atomic motion stops. Things stop vibrating. Things stop moving around inside at the microscopic level. When everything stops, we call that 0 Kelvin. Another word for that is absolute 0. Okay, here's a good time to introduce the term thermodynamics, because that's really what we're going to be studying in this module, thermodynamics. So think about what we studied in Module 5, fluid dynamics. There's that term again, dynamics. Thermo in this case means temperature or heat involved, right? And then dynamics is, remember, motion. Just like fluid dynamics was the motion of fluids, which included liquids and gases, same thing with thermodynamics. Here we are talking about the motion, the flow of heat energy. And we have to make a very important distinction between temperature and heat energy. Okay, we've already discussed that temperature is the average kinetic energy of the atoms, particles, molecules in a substance. It's an average. Thermal energy is the total amount of heat energy available with all those particles and such. If you add them all together, that is the thermal energy. So in a sparkler, for example, a sparkler is really, really hot. You know, those little sparks come off a sparkler are really hot. How do we know? Because they're glowing. Those little sparks are there. It's a certain number of molecules of sparkler material that is so hot that it is producing visible light to our eyes. It's glowing hot, perhaps around 2000 Celsius. That's the temperature of that spark, meaning that the average kinetic energy of the particles in that spark, let's call them sparkles, is 2000 degrees Celsius, really hot. However, the total amount of thermal energy available in that spark is not that much. Why not? Because there's not that many particles, molecules in that sparticle. And therefore, when that hits your skin, it might be somewhat uncomfortable, but it's not going to produce third-degree burns. And that's because the amount of energy that sparticle has available to give to you is relatively limited, not by the fact that the average kinetic energy is not that great, but because the total number of molecules in that spark is relatively limited. I had a high school chemistry instructor who, rather than posing the question, what is heat, he would say, there is no such thing as cold. Cold is simply the absence of heat. What you're going to notice is that once you understand what heat energy is, what thermal energy is, one of the main rules of thermodynamics is that heat energy always flows from where it's more concentrated, where it's hotter, to where it's less concentrated. So when there's a greater reservoir of heat energy coming into contact with something that has less heat energy, the heat energy is going to flow from the hotter object to the cooler object. Again, this is a good slide to kind of highlight the difference between temperature and thermal energy. Let's take, for example, let's say we've got, instead of two pots with different amounts of water, let's imagine we've got a little microbus, one of those tiny little buses with, full of kids, and then we got a big old school bus full of kids. Obviously more kids on the big bus than on the little bus. And let's say that we go ahead and get a pound bag of those M&Ms and just throw them in there and telling the kids they need to divide them up evenly. Well, can you see that the kids on the microbus are going to each wind up with more M&Ms than the kids on the big old school bus? Because it's the same amount of M&Ms being added to each bus. However, in the microbus, there are fewer kids over which you need to divide the whole entire bag. Same thing here with this demonstration. There's this question about how much the temperature would change when you add equal amounts of heat to each of those pots. Have you ever noticed that the box of a McDonald's pie does not say warning, crust may be hot? It only says caution, filling may be hot. They both came from the oven. When the cashier goes and grabs your pie, they're coming from the oven. They should be at the same temperature, and yet it's not the crust that's going to do damage, it's the filling, and that's because the filling has a higher heat capacity, which means that it takes more energy to heat up the filling to that certain temperature than it does to get the crust to that certain temperature. And of course, that thermal energy then stored in that filling, when you start eating it, is going to flow from where it's more concentrated to where it's less concentrated. It's going to flow from the filling to your tongue. And because there's more energy that's going to start flowing from the filling to your tongue, it's going to do more damage as opposed to the crust. The crust doesn't have as much thermal energy in it, and therefore is less likely to do damage to your tongue. As I mentioned in Module 5, my background is actually meteorology, so anytime that a science topic really hits upon weather or climate, I get really excited. And specific heat and the fact that water has a huge specific heat capacity, or a huge capacity to absorb heat energy, that's really what drives weather and climate. And this is particularly true when we consider the seasons. Now, hopefully, if I were to ask you, why does the Earth have seasons? Why is it warm in the winter, warm in the summertime, cold in the wintertime? Hopefully, you do not say because the Earth is closer in the summertime and the Earth is farther away in the wintertime. Simply not true. To get a full explanation as to why that is, you'll have to take my astronomy class, I suppose. But here's my globe, and it turns out that yes, indeed, the Earth's orbit is essentially a perfect circle. It's almost always the same distance from the sun. There are slight differences. In fact, just to completely blow the proximity explanation out of the water, it turns out that the Earth is actually closer to the sun at January 1st, or early January, the northern hemisphere wintertime. And it's farthest away from the sun in early July, the northern hemisphere summer. So if you thought that it was proximity, that's completely wrong. The reason why the Earth has seasons is because it is tilted. It's tilted with respect to its orbital plane, the way the Earth goes around the sun. And it turns out that in January, like I said, the Earth is a little bit farther away from the sun. I'm sorry, the Earth is a little bit closer to the sun than in the summertime. But the big difference is that the northern hemisphere, which is up this part up here, is tilted away from the sun. And it's the southern hemisphere that's tilted toward the sun. That's why we have it's warm in January in Peru and Bolivia, parts of Africa, right? That's why. It's not because of proximity, but simply because of the angle, the fact that the southern hemisphere is tilted toward the sun in northern hemisphere wintertime, January. As the Earth orbits around, by the time it gets down to the other side of the sun, now in July, the northern hemisphere is tilted toward the sun, and the southern hemisphere is tilted away from the sun. So for the northern hemisphere, July is summer. For the southern hemisphere, July is winter. That's essentially the basic reason for the seasons. Now, like I mentioned, the Earth is actually a little bit closer to the sun in January than it is in July. So you might think, well, gosh, in the southern hemisphere, they should have really extreme summers, because not only are they tilted toward the sun, and that's why it's summer for them in January, but they're actually a little bit closer, 91.5 million miles away from the sun, compared to 94 or 94.5 million miles. That's how far away the sun is in July. So why are they really, really hot in the summertime? Look at the screen, or look at this globe. Notice what the southern hemisphere is made up of a lot of. It's a lot of water. There's not a whole lot of land mass in the southern hemisphere compared to the northern hemisphere. See how much more land there is in the northern hemisphere. And it turns out that's a big, big influence on the climate. Despite you would think that, yes, the southern hemisphere summers should be warmer because they are closer to the sun than northern hemisphere summers. But it's the difference in the amount of land mass. It takes a long time and a lot of energy for water to heat up, and therefore it's not as big of an influence. Now, in a long time from now, because the Earth does change its eccentricity, and eventually the northern hemisphere is going to be perhaps closer to the sun in northern hemisphere summertime, July. Then you might have more of a influence on the climate. But until then, the proximity is really not an influence largely because it's not only a couple million miles and the southern hemisphere has a lot of water in it. The same reason that it takes a long time for water to heat up, you've probably experienced that if you've ever waited for a pot of water to boil. The same reason that it takes a long time for water to heat up also means that it takes a long time for water to lose its heat. And therefore, water and an ocean current can actually carry heat energy tremendous distances. Point of fact, the Gulf Stream. The Gulf Stream keeps Western Europe and Northern Europe much warmer than it normally should be for the latitude that it is at. This is a graphic that I designed a couple of years ago when I worked at USA Today, right before the British Open. And it was partly inspired by the Gulf Stream and the fact that, yes, parts of England are much, much warmer than they should be compared to, let's say, parts of interior Canada. And it's because of the warming influence of the Gulf Stream. The Gulf Stream takes warm water from the Caribbean and moves it across the North Atlantic to parts of Northern Europe and releases that energy, and therefore it moderates the temperature in Northern Europe compared to equivalent latitudes at other locations such as interior Canada. This is another weather graphic that I created at USA Today, and again, this kind of was ripped from the headlines. I think I read about some accidents in parts of the nation's heartland that were occurring during a heat wave, and the reason being that the highways were getting so warm that they were actually buckling, and people were flying along at highway speeds, hitting these bumps and losing control of their vehicles. And most of the time, expansion is designed into a roadway. The materials are designed to expand, bridges are designed to expand, but sometimes the expansion is even larger than the amount that was designed for. That's when you run into problems. But again, it's another example of this principle of thermal expansion. Not only does thermal expansion explain why thermometers can work, but thermal expansion is built into products that we use every day. If you recall back in Module 5, I mentioned this unique property of water. Most substances get smaller when they get cold, therefore they become more dense, or they become larger when they get warm and become less dense. Water is unique in the sense that once you get it below 39 degrees Fahrenheit or about 4 degrees Celsius, once you start cooling water below that, it actually becomes less dense. So that's somewhat unusual when you're cooling something and it's getting less dense. That's relatively unusual, and that is due to the unique bonding properties of the molecules within water. So this is a graph, and it's actually a pretty cool graph, no pun intended, of essentially the density of ice. Notice we're dealing with a 1 gram sample of water. And of course, density is mass divided by volume. So notice what's going on here. We're not changing the mass. The amount of water is not changing. But what is changing is the volume of that 1 gram of water. So as we go from, and notice this big graph shows water vapor. So you got really hot water vapor. As it cools, it's becoming taking up less volume. No huge surprise. Then notice there's a huge change when it goes from being from being water vapor to liquid water. And then as you cool it from 100 degrees Celsius, boiling point, cooling it, notice that yes, you do have a contraction, which is pretty par for the course. Things do tend to get smaller as they get cooler because the molecules get closer together as they lose energy. However, notice this little box. This little box is broken out over here. And we notice that as we drop down, eventually, so we're cooling until we get to, notice 4 degrees Celsius, that magic number, about 39 degrees Fahrenheit. At that point, water has reached its densest. In fact, it is 1 milliliter per gram, or vice versa, 1 gram per milliliter. It's got a density of 1 at that moment. Fresh water at 39 degrees Fahrenheit is at its densest. Then as we continue to cool it, notice what happens. It starts to get a little larger. Therefore, since it's the same mass and a larger volume, the density is now decreasing. And then we see a big jump then once we get from 0 Celsius water and we now freeze and become 0 Celsius ice. Notice that now the volume really increases, and therefore the density really decreases. And as we continue to cool the ice, it gets slightly denser. But water is at its densest at 39 degrees Fahrenheit. Okay, so let's think about a pond. Let's think about a pond that is at 50 degrees Fahrenheit. That's about 10 degrees Celsius. So let's imagine it's fall, we're getting into the winter time. The pond is at 50 degrees Fahrenheit, 10 degrees Celsius, and let's say the outside air temperature is, I don't know, 30 degrees. So it's cold, right? Cold outside. Of course, with the water being at a higher temperature than the air, the water should start to lose energy to the air. Makes sense, right? Water always, or heat always flows from a great area of greater heat energy to an area of less heat energy. Another way of saying we're flowing from hot to cold. So you can understand that the pond would be losing energy to the air. In fact, where is it going to be losing it from? It's going to be losing it from the surface, correct? So the surface water will be losing energy to the air. Down below the surface, down at the bottom, there's no real heat loss. But the surface certainly is losing heat energy to the air. So therefore, the surface water then becomes 49, 48, 47, 46. It starts to cool down, right? But notice what would happen to the density of that water. If you understood the last graph, you would understand that the water at the surface now is more dense than the water deeper down in the pond, because that water is warmer compared to the surface water. And so, since the density of the surface water is greater than the density of the below surface water, you're going to have some overturning. The surface water is going to sink. Well, if the surface water sinks, there's got to be something that replaces it. So water from below upwells and takes the place of the surface water. So now you have 50-degree water at the surface again. But of course, the outside air temperature is still 30. So now that surface water loses energy, and therefore it sinks, and so forth and so on. And this process is going to go on until the entire pond is at 39 degrees Fahrenheit or 4 degrees Celsius, at which point all the water, whether it's at the surface or at the bottom, is at the same density. Now, remember, now you have 39-degree pond water and still 30-degree air temperature. So you still have a difference in heat energy. So the water at the surface is still going to be losing energy. But now notice what happens. As that surface water goes from 39 to 38 to 37 to 36, what can we say about its density? It is now less dense than the water down below. And therefore, it doesn't sink anymore. It stays at the surface and continues to lose energy until eventually it gets down to 32 degree or 0 degrees Celsius water. And then, remember, the outside air is still cooler, and therefore it continues to lose energy, but now it loses energy and changes phase. Because at 32 degrees, water can't get any colder. It's got to now change phase. So as it gives up energy to the air, now instead of losing, it doesn't change its temperature, but it changes phase. It gives off energy in the process of changing phase from liquid to solid. That's how ice forms on the top of ponds as opposed to forming from the bottom up. I hope you've had the experience of perhaps waking up on a cold winter morning and walking into your kitchen, and perhaps you've got the living room and the kitchen with different flooring. Let's say you've got hardwood, like that's in my house. I've got hardwood in the living room, and I've got tile flooring in the kitchen. And you'd even have a greater difference here if you had, let's say, carpeting in your living room and tiled in your kitchen. What do you sense differently when you put your feet on each of those materials? You would notice that, gosh, especially carpeting would feel much warmer, right, compared to the cold tile floor. So what's the difference? Because haven't they been both in the same room for a long time? I've got an example here of, even here in my office, and I've got a messy desk, but if I put my hand on my wooden desk compared to my metal filing cabinet back here, they feel different. despite the fact that they have both been in this office for as long as I've had this office. And even before I was in this office, someone else had this office. These things are at the same temperature, and yet they don't feel like they're the same temperature. And that has to do with conduction, the rate at which energy is flowing from my hands into those objects. So why do we wear clothes? Well, we most likely get arrested if we didn't. In my case, I'm wearing clothes in this office. In fact, not only am I wearing clothes, I'm actually wearing a windbreaker. And this is how I spend most of my days here in my office, because my office is really cold and I can't control, the building is automatically controlled, so I can't change my thermostat. So I'm stuck with a relatively cold office. My body temperature is greater than the temperature at which the building has been set. And so I'm going to constantly be losing heat energy to the room. And I don't like that. My nerves, my body, I get goosebumps. My body says, hey, knock it off. You're losing energy really quickly. Do something about it. And so I put clothes on, or in this case, I put on a windbreaker. My windbreaker is not really a heavy material, but what it is it's not very porous. It doesn't allow the air that's close to my body to escape, essentially. Now, a lot of us wear sweaters, we wear down jackets, and those types of clothing, they are thick and they've got a lot of stuffing in them. The reason why they have a lot of stuffing is to actually create a lot of air spaces. Same reason why you have insulation in your attic. It's made out of spun fiberglass. The reason why it's made of that really loose material is that it has a lot of air pockets, because air is not a very good conductor. It's a good insulator, which means that heat energy is not conducted, does not travel very well through those materials when you've got a lot of air pockets. Now, in this case, my windbreaker does not have very many air pockets, but it also does not allow air to escape from between my body and the outside world. And so essentially it's creating an insulating layer of air close to my skin. So as that air warms, it wants to rise, it wants to convect, as we're going to be talking about next, convection, but it can't because I'm trapping it. I'm keeping that air close to my body. But again, all this does is it slows the flow of heat energy from my body to the outside world. And that's the whole point of having insulation. And of course, we don't have a monopoly in staying warm or insulating ourselves. Animals do as well. In fact, animals naturally have insulating material that is called fur. What does fur do? Fur is essentially a way of trapping air close to the body. There's a lot of air spaces, a lot of air pockets in a dog's coat of fur, particularly a dog that typically is associated with colder climates, such as Malamutes and Huskies that would be used in, say, the Iditarod sled dog race. Those dogs have a really, really thick coat of fur in order to trap a lot of air close to their bodies. And of course, their mushers, their drivers, lay out straw for them to sleep on. Why? What is straw? Straw is essentially just tubes of air. Again, air is a lousy conductor. It's a very good insulator. It does not allow heat energy to travel as quickly from the dog to the ground or from the dog to the outside world. Conductor, insulator, which is better than the other? Well, it depends. So if you don't want to get cold, quite often an insulator is a good thing to have. But as we're going to discover in a next module, in fact, when we talk about electricity, it turns out that good conductors of heat are also good conductors typically of electricity. And poor conductors of heat are poor conductors of electricity. They are related because quite often what is the conducting material quite often are loose electrons. And that is a pretty common property of things that we call metals. Metals tend to have a lot of electrons that can move from one atom to another. They're called loose outer electrons. And not only can they conduct heat energy, but they can also conduct electrical energy. So, one is neither better or worse than the other, but we see this commonality that good conductors of heat are also good conductors of electricity for the same reason, because of the number of loose outer electrons they have. So we've already talked about conduction being a way of transferring heat energy directly from one object to another when they're in physical contact. When you touch a hot stove, heat energy is conducted from the stove to your hand directly. Convection is when you have transfer heat energy through the bulk motion of fluids. That includes liquids and or gases. So for example, a pot of hot water, the water at the top of the pot doesn't immediately get warm, right? How does it get warm? Well, it gets warm because the water at the bottom of the pot gets warm first, becomes less dense, and rises, and of course then the water in the top has to work its way downwards. So you have this overturning, and that's how you get the rest of the pot of water hot, is through a convection, a process of heat transfer using the bulk motion of a fluid. Or let's say if you put your hand over a candle. The reason why your hand gets warm, you're not physically in touch with the flame. What's going to happen is that the air near the flame gets hot, and it rises and hits your hand, and of course gives up some of its energy because it's hotter than the air that's normally around your hand. So that's another example of convection. A greenhouse, or let's say your car on a hot summer day, is a good example of a stifled convection. In a greenhouse, the sunlight comes in, and it comes in through the windows, and it heats the bench and the table and all that kind of stuff, and that stuff gets warmer, and then of course then the air in contact with that stuff gets warmer, and that air wants to rise, wants to leave the greenhouse, but it can't because it's stuck in the greenhouse, and therefore the air temperature in the greenhouse just gets hotter and hotter and hotter, because the convection that normally should happen with the warm and less dense air rising is stifled because it runs into the windows. So same thing with a car on a hot summer day. The reason why it gets so darn hot in there is because convection essentially gets stifled. So far we've talked about a couple of modes of heat energy transfer. Conduction, where you have direct contact between two objects. Convection, that's when heat energy is transferred through the motion of bulk fluid, such as liquid or a gas like air. But what about how does the energy from the sun, first of all, get here? Life on Earth would not be possible if it weren't for the fact that there was a sun relatively close by. But how does the energy get to us? Obviously, it's not conduction. We're not even close to being in physical contact with the sun. It's 93 million miles away after all. Convection is also not a possibility because space is essentially that. It's empty space. There's not enough gas to conduct the energy or convect energy from the sun, and therefore there's got to be another mode of energy transport, and that is radiation. That is the transfer of energy through electromagnetic waves through empty space. The electromagnetic waves, and we're going to learn more about this in a couple of modules, but it's not just visible light. It turns out that when we talk about light in science, we're not talking about just the stuff that our human eyes can see. It turns out there's all kinds of light, electromagnetic waves, that we can't see. We've got infrared light, we've got ultraviolet light, we've got X-rays, we've got gamma rays, we've got radio waves, we've got microwaves, etc., etc. All these are considered forms of light, just light that we cannot see with our human eyes. This is an important point. Anything that has temperature, anything that is above absolute zero, radiates a certain amount of electromagnetic energy. That includes you. So if we were sitting in a room, I could see you, not because of the fact that you're producing visible light. You're not producing visible light. You reflect visible light. The lights or the sun hit you and then bounce, and that visible light then either gets absorbed or reflected off of whatever clothing you're wearing, and then I see you because of that reflection of visible light. But let's turn off the lights. Let's turn off all sources of light. Let's put you in a dark room, no artificial lighting. Can I see you? No, because now there's no visible light available to reflect off you or your clothing and bounce into my eyes. Is there no light available? No. If I had an infrared camera, I could see you in that dark room because you have temperature. Your body is at 98.6. So you're not hot enough to be glowing in the visible spectrum. However, you do produce infrared radiation, which I could detect using an infrared camera. Okay, this graph looks a little bit complicated, but I'm going to try to boil it down for you. Any object that is above absolute zero radiates energy. And it turns out that the hotter the object, well, I should mention, it radiates energy not just at one particular wavelength or at one particular frequency, but at a range of frequencies. But it turns out the range always has a peak. The hotter the object is, the farther to the right or to the higher of the frequency is where the peak is located. So what we see here is we've got, let's say, 3 different stars. One star being this one that's kind of written in red here. At 1600 Kelvin is the temperature of this star. And it produces a whole range of light, and its peak is right there. We got another star that is a little bit hotter. It's 2400 Kelvin. Notice where its peak is. It's farther to the right. And we got a star that is 3200 Kelvin. That's farther to the right still. So it turns out that where the peak occurs is at higher and higher frequencies. Now, how would these stars look to us? Well, I should explain that visible light is made out of the visible spectrum, Roy G. Biv. So down this end, this would be our red end here. That's the red end of things. And then let's see, let me throw in green. And then we'll throw in violet here, purple. Okay, so as you can see, the first star that we mentioned, the 1600 Kelvin star, may be so cool that we don't actually see it. Because notice it produces a lot of infrared light and maybe some radio waves and that sort of thing, but it produces very little in the way of visible light. Now our second star, this 2400 Kelvin star, would most likely appear reddish, because notice when we get to the visible spectrum, it's producing a lot more red than it is violet, and therefore that star would appear reddish. Even our 3200 Kelvin star, first of all, would appear most likely brighter to us if they're all at the same distance, because it's producing more visible light. But notice that it's producing, again, a lot more red than it does violet. So this would still most likely be a reddish star. But if we continued on here, let's take our sun, for example. Our sun has a temperature of about 5800 Kelvin. And I'm just going to draw a make-believe curve here, try to follow so whoop, something like that. Notice that in the case of our star, notice where its peak is. It's farthest to the right. In fact, I put my peak in the visible, just for fun. But notice the amount of red that it produces is about the same as the amount of violet that it produces. And it actually peaks in like the green or perhaps the yellow, which is indeed what our sun looks like. Our sun looks yellow because it produces an almost even amount of all the different types of visible light, with perhaps a little bit more of a peak in the red and the yellowish or greenish area. But notice again, the temperature of the source determines where the peak frequency winds up being. Okay, so why do we sweat? It's a really interesting process. The body starts to feel too warm. In fact, the core temperature starts to climb too much and it starts to feel danger because the core can't get too hot. And so what it does is it shoots a bunch of water out onto your skin through pores. Now remember, water has a huge heat capacity. So by having water in direct contact with your skin, now you can have conduction. You can have heat energy being conducted from your skin to the water. And because water has a great heat capacity, it can be done. It can take the water on your skin can take in a lot of energy from your body. And of course, now that water on your skin gets warmer. And so remember how we talked about water having all these molecules, water molecules in there, and they start moving around. In fact, the average temperature of that water starts to go up, which means that the average kinetic energy of those water molecules is increasing. And so you have your really high achiever water molecules that are really zipping around, and you have kind of your average ones, and you got your slackers. Well, your high achievers are going to now start to have enough energy that they actually leave the liquid phase and become gas. And so that means that you have less water, you have evaporation there. Now, evaporation is a cooling process because think about, we've talked about average grade, right? The water there in your skin, or the water in the sweat, since you've lost the high achievers, now what happens to the class average when you lose your high achievers? When you lose all those A's out of the overall class grade? Well, the overall average drops. So the water droplet that's still left in your skin after when evaporation starts, the water droplet actually becomes cooler. And because that water droplet is cooler, now you've got a bigger temperature differential between your skin and the water left on your skin. So again, you can have more thermal energy leaving your skin and going into the water. Until, of course, that water droplet entirely evaporates entirely away, in which case it has to be replenished by more sweat getting onto your skin. That's why you have to, especially in dry regions, really have to watch your consumption of liquids. Make sure you do stay hydrated in the hot summer, because you will lose water very, very rapidly through the evaporation process. Okay, since we're talking about states of matter and changes of phase, I wanted to do a little demonstration that involves a cup of water. So this is just normal room temperature, straight out of the tap water. And what would happen if we just let this water sit around for several days or a couple of weeks, just in a classroom? Eventually what you would see is that right now it's about halfway full. I'm an optimist. But it would the level would start to decrease. Notice at room temperature even. And that's because the water molecules, they've got a certain temperature. We call it, it's, I don't know how warm this water is, 70 degrees Fahrenheit. That's the average. When we talk about temperature, it's the average kinetic energy of the molecules that we're talking about. So in this case, the average kinetic energy of the water molecules in this glass. But remember, that's just an average. So just like when in your classroom, you can have an average test score. Some are going to have a much higher grade, some are going to have a lower grade, and then you have just the average. So the majority of the water molecules are around that average kinetic energy. But there are some really high achievers, and there's some real slackers in there. Well, it turns out the high achievers have enough energy that they can actually leave the liquid phase and become gas water molecules, otherwise known as water vapor. Even at room temperature, there are still some of those really high achievers that have enough energy they can escape the liquid phase and become the gas phase. That's what we call evaporation, when you go from being liquid water to being gas water or water vapor. That is not to be mistaken for boiling. Boiling and evaporation are not necessarily the same thing. Boiling is when you have water molecules turning into gas molecules or water vapor within the water itself, within even at the bottom. Those water molecules have enough energy that they can become gaseous and then leave. Right now, the evaporation essentially occurs mostly at the surface. You have water molecules at the surface that are high enough achievers that they can become gas. Boiling is when even water molecules within the liquid, well below the surface, can actually turn into a gas. That's why they form those little bubbles, which then go off to the surface and leave as water vapor. So, why do I make such a big introduction? Because we're going to do a little demonstration here. We're going to put our water in our good old bell jar, and I'm going to remove the air. So right now we have air molecules in the bell jar, but by putting it on this platform, I can remove the air molecules. And this is not unlike traveling to higher elevations. So I'll go ahead and turn my vacuum pump on. We'll see if we can get a good seal. I may put a little extra grease around the base. So again, prevent air molecules from. One thing that I should point out, this vacuum pump does not add any energy to the system. All we're doing is taking out air molecules. We're not adding any energy to the water. So it came out as room temperature water, or
even cooler than room temperature water. And I'm not heating it up whatsoever. There's no hot plate here. All I'm doing is removing air molecules. And what we should see, if we look really carefully, notice anything? And then we're looking through the bell jar. What you should notice is that yes, indeed, there are little bubbles forming inside my water here. Coming to the surface, my water is boiling. Without adding any heat energy whatsoever, we were able to make this water boil. I found a famous mountaineer named Edmund Hillary, who was a British guy. Sir Edmund Hillary was the first one to ascend Mount Everest. And his biggest gripe with the climb was that he couldn't make a good cup of tea. And that's because, good British gentleman that he was, at tea time he would start a fire, put a pot of water on the fire, and his water would boil, but he started to notice that as he climbed, his water was boiling at lower and lower temperatures. And tea leaves need to steep at a certain temperature or the tea doesn't taste very good. And so he was discovering that, yes, there was a reduction in the boiling point due to elevation. And that was a real problem for him. So now we see why. We've essentially created a high altitude experience. When I let my air back in, I just want to prove to you that, again, we've not added any extra energy to the system. This is not a hot plate. All I did was take air out of the bell jar. So very much like climbing to higher altitudes, there are fewer air molecules there. Same thing with my artificial creation of that situation in the bell jar. Remember, this is just boiling a few seconds ago. Boiling water. But it was boiling at room temperature or below, because I was able to reduce the air pressure pushing down on the surface of the water, and that allowed more water molecules to become gas molecules.